marked some pointers. So we'll start with fundamentals. I'll talk about the most important idea, which is a conditional probability distribution. And then we'll talk about one particular language which we'll be focusing throughout the discussion today, which is English. We'll look at some interesting developments in the interface design based on the traditional language models. Then we would move on to an interesting concept of the sampling distribution and how do I talk about goodness of a particular language model. So before I actually do something with language model, or I design or I train a model, first thing I would like to understand is given two models, which one is better. Correct. So I'll talk about perplexity, and then I'll talk about the large language model as such, what they are today, where I'll focus on transformer architecture. There are other generative models which I'll not touch upon, like diffusion models. So we'll focus today only on the transformer based architectures. And then maybe if time permits, we'll talk about some capability and limitations of LLMS in terms of what they can do, what they can do good, and what is it that you should not expect from them. Correct. So with this, let's start with the fundamentals. So this is my pet example that I typically give when I talk about language model as such. There is a nice story, War and Peace by Leo Tolstoy. It's a classic, big book, and every language has a classic, and the classic typically helps you build your vocabulary. It is expected that if you are reading a classic from your own language, perhaps almost all the words of your vocabulary would be part of this book somehow. So Leo Tolstoy, a good example. War and Peace has almost every English word that you can think of. Correct. And so it's a good starting point. As a child, when we learn languages, the way in which the language acquisition starts is through speech. And before speech, it is about hearing. Correct. So we listen to a lot of disconnect हो रहा है बार बार. Okay. So is it visible now or has stopped?
Yes, sir, visible. Your screen is visible.
Okay. So as a child, when we acquire language, we usually listen to a lot of utterance of words, sentences, and then gradually we try to imitate. We try to reproduce the same using our own vocal tract. And in the process, we learn phonetics and other things, but still we do not know what are the meanings of each of this word that we utter. Correct. Then gradually you also start collecting few words, make a sentence, and given the context, a particular sentence is used multiple times. So somehow we get a hint that whenever this happens, I should speak this way. I should uh, pronounce this word. I should pronounce this word this way. So all the emotions and everything becomes part of your contextual scenario, and you try to you actually do not try, but you learn the language in this fashion. And when you are around 6-7 years of age, suddenly you start taking classes where you are supposed to learn alphabets, you start writing, you start reading. And that is the phase where your vocabulary starts developing. Correct. So till that point of time, only things which you have heard is something which you are able to utilize in your communication. Correct. So early days of your childhood are typically driven by the need of communication for survival. So food, you are hungry, you want to go out, you want something. So those are the things that you want to do when you are young, too young, essentially toddlers. Then gradually you become literate in terms of writing and reading, and that's the phase when you actually have a lot of growth in terms of vocabulary. Now, vocabulary does not guarantee that you will also acquire grammatical constructs. So that does not guarantee that you will actually be able to compose a sentence or a paragraph on your own. Correct. But still, it's a phase where you acquire lots of words and their association with the actual events or the items or the objects. So this association building starts. Then comes a phase when you start reading and then writing. So you read and then you express your views by writing. So this reading activity actually is the most important activity which builds your vocabulary. And more you read, more it is likely that you will become a good communicator. Correct. Both in terms of writing and speech. So whatever we do during this phase of our language acquisition. Now the question was, is it possible that the same sort of pedagogy is used for training a machine which can produce meaningful sentences on its own? Correct. And this is the journey from early language models to large language model, and that's what we will be talking about now. On an average, on daily basis, when you start reading, 8 to 9 words is something which you start acquiring on an average, and then gradually this hits a ceiling, and interesting thing happens. The interesting thing that happens is the growth at which your vocabulary builds. Sometimes it exceeds the number of distinct words that you have read. Now, why this? Because gradually the context in which you are reading and the context words. So when you read, there is a causality. You read one word after the other, correct? And then you also complete a sentence and then try to make sense of a particular word which is used in a sentence. So given the context, given lots of words, you try to figure out why this word was used inside this sentence and what was the context. So when you are doing this, along with your primary focus word, other words also become part of your vocabulary. So that's why after a while, when your reading improves, the growth at which your vocabulary is built is much more than the rate at which you read. This is something which is very, very interesting. And uh, this is something which can be put in one-to-one analogy with our language models also. So let's formally start discussion on the idea of the context, idea of the causality. And before we do that, I would like you to uh, just let me know if uh, you have any questions. It is better you interrupt me early. In the end, we may not get sufficient time. So whenever you have a doubt or you have a query, just unmute yourself and let me know what is your query. Correct. That is the easiest way to progress further. Okay. So what I have done is I have put up another window, and in this window, this is another of my favorite examples. So I'll keep giving you examples which are of my uh, kitty of favoritism. So what you see here is a sort of a pixelated or pixelated square of size 27 by 27. And any guesses, by the way? So I was talking about war and peace. Then I'm supposed to talk about conditional probability, and I'm showing you a nice pixelated 27 by 27 image. So any guesses what this could have been? Those who know this, I think they might have some exposure to what we refer to as a transition probability matrix. So what
Sir,
I have done
screen
here
is
is,
not visible. Screen is not visible.
okay, so whenever I switch, there is a problem.
Just share it with entire screen, sir.
Entire screen. Okay.
Yes. Not just window, rather entire screen.
Then I would not be able to look at you all. So, ठीक है. So I'll keep sharing. Don't worry. So this 27 by 27 image essentially is some sort of a transition probability where going through Leo Tolstoy, we try to figure out, I'll give you an example. I have a sentence which says life is like a box of chocolates. Correct. Now, what we do, we try to figure out from this sentence how many times in this sentence H follows T. So how many times do I see that H is after T? And the answer is 1. How many times H is after C? 1. Similarly, I after L twice. If I try to figure out all the pairs of characters from this sentence and prepare a table which says that how many times a particular alphabet follows a particular alphabet. So essentially, I am looking at some sort of a bigram. Bi means 2, gram means collection. So bigram occurrences in a particular sentence. So what I have done is, from this book, Leo Tolstoy, War and Peace, I have created this transition occurrences. I have counted all of these transitions character by character. And then I have normalized them, saying that a number of times uh, a particular alphabet comes after A to Z should add up to 1. So some sort of a probability saying that whatever outcomes are there after T, all of them should add up to 1. The probability with which H comes after T, A comes after T, B comes after T, C comes after T, up to Z comes after T should all add up to 1. Reason being, something or the other has to come after T. Correct. So that means it's like a probability score. More bigrams I observe of a particular type in a sentence, more likely that particular pair is in the language. Correct. So using this, we created this table, and what you observe is first few characters starting with A. So if you look at first row, it is A, then B, then C, then D, up to Z, and then there is one additional thing which I have kept for the extra characters like space, full stop, comma, exclamation, question mark, inverted commas, and many more. So things which are not alphabets are put in one class, one basket. And so 26 alphabets plus one additional, that makes it 27. So I have now 27 by 27 transition probabilities. And what is it that you see here which is brightest? This part, correct? This position looks like the brightest sort of probability value. So white means closer to 1, black means closer to 0. So here white essentially means 1, yeah, and black means 0. So what you see here is this is the brightest spot which represents transition from Q to U. Have you ever seen a word which starts from Q and after Q there is A? Have you seen this type of a word in your entire life? Q followed by B? No, not possible. What I have seen is Q followed by U. This is something which I have always seen. And that means probability that U is after Q is maximum. So given that I have Q as a character, the next character has to be U. There is no other possibility. Queen, quiz, quack, Q. Everywhere you see that U follows Q. And that is something which is highlighted by this brighter spot. That means, as simple as these characters look, the moment I have English as a language, these characters, in terms of their transitions, they follow certain statistics. They are not arbitrary. They follow certain basic statistical properties. And this is something which we refer to as a bigram language model, where where I would say, what is the probability that the given character is Q, the next character would be U, and this is equal to 1. Correct. Given that at particular instance of your index, your sentence position at T, I have the alphabet Q. What is the probability that at T plus 1, this alphabet would be U? And this probability is 1. So this is the conditional probability that we typically talk about when it comes to language models. So language model has many dimensions. So in computer science, you have learned about regular languages, languages which are represented by state space, essentially automata sort of thing. And all your compiler designs and everything is based on that sort of formal languages, correct? But what language we are discussing right now is like a slightly more sophisticated version of it, where we expect the language to have some sort of uncertainty involved, and there are probabilities with which you can define the transition rules. So it is more like a natural language, and the probability depends on the context. Here the context for bigram model is given that the current alphabet is xt, what is the probability that the next alphabet would be xt plus 1? Yeah, any questions up to this point? Now nobody stops you from saying that why only xt is equal to q. Why only take one transition? I can always talk about more than one transitions. So I have xt, then I have xt minus 1. In fact, I can go up to x0, the starting point of my sentence or my word, and then I try to predict the next character. So I have, let's say, 10 characters in my word. I hide the last one. I reveal the first 9. Can you tell me what will be the third character? That's how we put this context into place. So all this x0 to xt, they are the context characters. And xt plus 1 is the word, is the alphabet which we try to figure out. Now, the way in which I have talked about this is I start from index 0, build upon this, reach up to t, and then I try to infer about t plus 1. Now, all these 0 to t are before t plus 1. So this has some sort of a causal relationship. Cause effect essentially means something happened because of which something is observed. So up to t, I have observed the sentence. I have observed the sequence of characters. I want to find out what happens at t plus 1. So this is the causality with which most of the one-sided models would work. Now, there are models where I can actually talk about your capabilities. Let's say, let's try. Okay, let's try and figure out what is this. So I have set up a small word. You are required to tell me what the blank spaces could be. Entire screen ही कर देते हैं, चलिए. Okay. So I have a word where I have no idea about the blank spaces. Can you help me fill in these gaps? I understand after lunch the sessions are typically quite difficult to sustain, but let's participate once.
Participants are requested to be interactive with the sir.
Can they unmute themselves or no?
No, sir. Actually, it has done the
अच्छा,
setting
अच्छा,
of
अच्छा.
mute itself. They can have a say interaction with the chat box through the chat box.
उसके लिए मुझे चैट बॉक्स देखना पड़ेगा. Okay. So okay, we already have an answer. Okay, ठीक है, understood. So wonderful. So now what we see here is there is no causality in place. So there is no sequence in which correct. So we have a wider scope of word context. Now context is not limited only to previous, not limited to previous or only next characters or words or events, correct? So it is not limited to this sort of idea that what comes after, what comes before. It's a wider context. So we have to keep this in mind when we will gradually talk about large language model, which has a context where context is like non-causal, correct? So so far so good. So now I have a conditional probability table with me, and I can talk about not just a bigram model, I can talk about any n-gram models. N-gram means I can have a probability distribution estimated from the text of large corpus, correct? T minus n to t minus 1 to t minus n. So I have n previous alphabets. I want to predict the next one. This is called an n-gram model. Now, the way in which this happens is at xt, you might have 26 different possibilities to choose from. The one which this model would pick for you is the one which has the highest probability value, correct? Now, instead of choosing the one with highest probability, what if I sample this? What if I sample this distribution? So the moment I do this, I sample this distribution rather than pick the one with highest probability. This starts entering into the domain of generative AI. I'm just pointing out the differences between the idea of a model, language model, and the generative task. So in generative task, we do not expect a model to give us one answer. Every time I run the same piece of uh, text generator, it will give me different sequence of words, different sequence of alphabets. And that's the part which we refer to as generative. So there could be many words which fit into the same context. But sometimes the model would use word one, sometimes it would refer to other word with some different probability. So rather than picking a word with highest probability, we pick a word which comes out of the distribution. So I sample this distribution, I generate a random number, and from this random number, I decide which alphabet or which word would be the next one. So whatever I have been discussing so far was based on the alphabet. Now you can think of each of these xt minus 1, and so on as a sequence of words rather than sequence of characters. Sequence of characters is now sequence of words. So instead of saying that xt is a character, now I say xt is a word. Xt minus 1 is another word. So rather than keeping track of conditional probabilities, which are for alphabets, which are A to Z and then some special character, what we have is a collection of all words. So in English language, any guesses what is typical size of the English vocabulary? Size of English vocabulary? आपके पास डिक्शनरी होगी, you must have access to a dictionary. So how many total unique words are there in the English dictionary, roughly? Q is the context, sorry. X is the word or the character. Sorry for that. This was answer to a query which was there in the chat box. Yeah, around 50,000. Chalo, theek hai. We'll start from there. So the size of English vocabulary is around 50K. So 50,000 words are there roughly. So that means if I go by bigram model, what would be the size of the matrix? It will comprise of 50K by 50K matrix. And what is the storage required for this? Each of this is a probability value. Correct. Mohit is suggesting there are 6 lakh, over 6 lakh words. But if you look at the words which are used in practice, they are of the tune of 40,000, 50,000. Many of the बार बार बंद हो रहा है, कुछ तो गड़बड़ है. Many of the words are essentially stop words which we do not uh, use in terms of its meaning. So there are some connectives, there are some words which are articles. So some of the words are not meaning communicating devices, so they do not carry any meaning. So if I remove those things, then roughly 50 by 50. And this is just for example. And each of this entry in the matrix, ijth entry, would be a floating point number, a double. So typical size of a double is how many bits? Integer is unsigned integer is 8. What is float? Double कितने bits होंगे? 16 bits, 32 bits, 64 bits, could be anything. Correct. Let's start with 64 bits. Each entry requires 64 bits. So essentially the size of this would be 64 bits multiplied by 50,000 multiplied by 50,000. This is the size of your bigram model. What if it is trigram? Another 50,000 gets multiplied to it. Correct. So essentially n-gram model has a space requirement of this many bits. Now this is pretty large. This is too large and difficult to handle. So there has to be a way to essentially work with some sort of an approximator which will approximate this conditional probability table. So I'm now using the word too large a table, store and recall. It is one thing to store data, it is other thing to recall the data, correct? So essentially if I want to find out a particular ijth entry in the matrix, the cost of reaching that particular entry is also prohibitive. So we want this table to be somehow stored in the form of a function. And what is this function is supposed to do? It should approximate the conditional probability distribution. So all that is done, in language modeling is to essentially large language modeling is to find out a good function approximator which will approximate your conditional probability distribution. This is the ultimate one-liner for large language model. They are the function approximators, and the function which they try to approximate is the conditional probability distribution. Fine. I think this is something which I can skip. This is important, so I'll talk about it. You might have seen Dasher. If not, then I would recommend that you should have a look at it. So David McKay, he is actually no more. He is a coding theorist, and he has developed an interesting sort of interface. Wow. He has developed very interesting sort of a tool which he calls Dasher. Have a careful look at what is happening. Again, have a look at it. It starts from the cursor here, the crosswire.
Sir, again the screen is not visible.
Oh,
Yes, now it is visible.
so what you see is now it will start writing on the interface. You see a crosshair, and there is a cursor, the plus sign. It starts traveling, and wherever you go, the right side, the different sizes of rectangles appear, and the sizes are proportional to the probability with which they would come next. And this interface was designed for people who could not actually. Okay, so I think this is sufficient for you to have some idea about Dasher. So, so what it does is it allows the user to use minimal muscle efforts to write English language. And it's a good example of how diagrams would typically work, correct? So it is not just about using language model for specific coding task or specific report writing or something of that type, grammar correction, but generative AI or the language model can actually be used for designing the user interfaces also. And this is not today, this was done in 2001 to 2005. So it's a good sort of a toy, uh, and it's an example of how language models can help you design your next generation systems, correct? So with this, I think now we have understood word transition probabilities. We know what is n-gram language model, and we are ready to deal with our large language model comparison sort of idea. So before we proceed further, any questions, any doubts up to this point? कोई सवाल? What is the actual use of this? So if you go to the Dasher's webpage, there are interesting use cases. One of the use cases, when you are wearing a headset, you are in a metaverse, so you have a headset, and you don't want to utilize any of the because most of the things happen using gesture and the eye tracking devices, correct? So imagine that you are in that sort of a metaverse, and your eye movements are being tracked by looking at a crosshair. By looking at a crosshair, you can actually write down the English language. You don't have to speak, you don't have to use your hands. Just by changing the way you look at scene, it would start writing, correct? So it is some sort of input interface which allows you to enter language in text form. That's the most important use case of Dasher. So those who are physically challenged, they can actually write English, and this is something which is very important. I hope that helps answer your query. There are many use cases, but this is one of them. So yeah. So in summary, what I would say is not only VR. Suppose you have a mobile phone. Mobile has a nice possibility. So when you have a mobile, you have lots of sensors inside mobile. Uh, what are the different sensors that you have in mobile phone? The one which tells you whether it is up or down, correct? Because when you rotate your mobile, not camera, when you rotate your mobile, it changes the orientation of your phone screen, correct? How does it know that it is tilted, it is rotated? What is it that's inside the mobile phone? क्या होता है? Gyroscope. छोटा सा gyroscope होता है अंदर, not camera. There is a gyroscope inside it, and it's a sensor, yeah. So you can actually use your mobile phone. You can tilt your mobile. ये वापस चला गया, अरे यार. You can use your mobile phone in a particular orientation. When you tilt it, it starts writing. So you don't have to enter, you don't have to use your fingers or thumb. You just tilt your mobile and English sentences are being written. You tilt your mobile phone in a particular way and it starts writing the English text. So these are the things which can happen with language models. Another important aspect is it can correct the errors. So when you are typing, without you noticing the error, it corrects automatically because it knows that this word does not exist in the English language. So it should be this, not that. So most of the current day cloud-based interfaces, for example, Google Doc है या तो फिर आपका Microsoft जो भी document handler होगा, all of them they come with this capability. They propose that there is an error. If you want, I can correct it for you. Overleaf hai. So all of this they come with this type of language models. So I gave you an example which was not a routine example of a VR headset, but you can imagine use of this almost everywhere today. Almost everywhere this has an application. So to summarize, it depends. Dasher, how do you use it? So how do you provide input to Dasher? Through gyroscope, through eye tracking device, through muscle movement. So it depends on what is the input to the Dasher. Dasher is like a small interface where you can provide input through various physical sensations, correct? So facial expression also could be one of them. Eye expression is not a correct word. It's typically the movement of eyes. So expressions are slightly different. So when you look at a screen, let's say center of the screen, your eyeballs will be at a particular location, correct? When you look at the top right corner of your screen, eyeball movement would be there. So the trackers would typically track these eyeball movements, and accordingly the crosswire would be moved in a particular direction. Is that clear, Dhananjay? ठीक है, अब थोड़ा बहुत आइडिया बहुत है, ठीक है. Then comes the summary part of it. So summarizing this is easy. I would request one of the participant to summarize, because I also would come to know that where do we stand. So, ma'am, can you unmute one of the participant or few of the participants so that they can unmute themselves?
Yes, sir. Yes.
Whatever happens next depends on whatever you understood till now. So, and it was not difficult. I hope it is not difficult. I have not used any mathematical expression, nothing. Correct? अच्छा. Anyone who would like to? अब इसमें से मैं मोहित को जानता हूँ, तो मोहित से बात कर सकता हूँ. मोहित, summarize the discussion so far.
Participants can unmute yourself and interact with the sir. Actually, few people are new today for the LLM, sir. So might be these concepts are heavy for them. Few people are new to LLM.
हाँ, ठीक है. We have not talked about LM at all, so don't worry. This is basic
Even
probability.
the even they are new to bigrams, n-grams concepts.
Okay.
Participants can unmute yourself and summarize the session till now, whatever sir has discussed.
Yeah. Hello.
Anji, yes.
Sir, from your discussion, what I understood is we are trying to predict from the previous state, uh, and we are predicting what will be the next state, or we can say from x underscore t. We are predicting from x underscore t minus one to from 0 to t minus 1. So these kind of things we are trying to predict.
So I think one general thing that I missed in the early part. See, this X is like a sequence. X0 is first character, X1 is second character, and so on. Or X0 is first word, X1 is second word, depending on the required application. If it is a word-based system, XT is a word. If it's a character, XT is a character. And there is no state here. What we say is, I know what are the previous 5 characters or previous 5 words. I want to find out what is the probability that the next word would be 1. Next word would be ONE1, given that previous 5 words were this. Correct? So that is what we learn from the known text. So I have, let's say, a big book. I read the big book, and I read that every time after these 5 words, the 6th word is always 1. So that helps me understand that whenever I see these 5 words, the probability that the next word would be this is the highest. And this is something which we learn from the known English corpora. essentially this is what is done when we read. When we read, we also do the same thing. We read a sentence and somebody hides, let's say, the next words. We try to predict how likely it is that the next word is this. And then we pick one out of this, which has the highest probability. Correct. So the same thing is true for a small language model, where the language is learned based on the transition probabilities of the words. So 2-gram model, 3-gram model, n-gram model. So if I have 1-gram model, I have one word with me and I want to predict what is the next word. In 2-gram case, I have two words with me. I want to predict the third one, and so on. So for n-gram model, I have previous n words. I want to predict the n plus 1th word. And when I say I want to predict n plus 1th word, it does not essentially predict the word. It predicts the probability with which a particular word can come in n plus 1th position. How likely it is that this word would be n plus 1. I hope this clarifies the notations also.
Yes, sir. Thank you, sir.
And then we said that this table becomes quite large as the number of words increase in size. The vocabulary size is large, and also increases, then this becomes pretty prohibitive. This is like a huge table to store. And so instead of storing this table, what do? We approximate this table with the help of a neural network type of architecture, where I input the particular context, I get the output in terms of conditional probabilities. So I supply this n words as input, I get the output, which is a probability on the vocabulary. Out of 50,000 words, I get the probability for each of these 50,000 words. So input is 5 words, output is probability distribution on 50,000 words. This is what I get in the output. Correct. So that is my conditional probability distribution, which is essentially captured by the neural network. And when I use this neural network for generative task, where instead of identifying a word with the highest probability, I sample this distribution. So I essentially generate a random number and pick one out of all these words based on the probability values. Then this becomes a generative model. So this is what is referred to as generative AI. So now you have converted your LLM into a possible generative mechanism to generate text. Okay, good. Yeah, I hope now it is clear. A little easier path for us, because I'm pretty sure that you have understood the concept well. The other notational issues, you can fix them. Is this the how AI is working by using LLM? Question is not clear, by the way. So can you just unmute yourself, Dhananjay? पूछ लीजिए क्या है ये सवाल.
Dhananjay sir, unmute yourself. Hello.
Yeah,
अच्छा,
hi,
आपने
sir.
कभी देखा है? हाँ, पूछो
Good
पूछो
afternoon.
पूछो. Good afternoon.
Actually, I'm confused with some background thing. Is this is a LLM is how GPT is using LLM while I'm asking some questions to GPT. So GPT is using
Yes.
this
Yes.
LLM and show the results. That is
Yes. So
the
when you
main thing of it.
correct. When you ask the question or when you
Okay.
write down any prompt in GPT, GPT would take that prompt and will first ask a question. What is
Okay.
the probability distribution on the first word? So it will get a
Just like
distribution of it will get probability values for 50,000 words. Then it will sample out of 50,000 and a first word comes in. Then it would say, this was the prompt given by the person. This is my first word. what should be the second word. Again, it will give you
Okay.
probabilities for 50,000 words, and again, it will draw one out of them. So this is how the
Okay.
text is actually built, and that's why we refer to this as generative model. So it actually
Okay.
generates the text word by word.
For example, we can say if I type a morning, so
Yeah,
ChatGPT will answer me good morning. So
it
it is
depends. So it depends. Every time it need not give you good morning.
hmm, just
Every
example.
time it will draw. Yeah, it will draw a number, and based on the number, it will pop out a word. Correct.
Okay. Okay. Got it. Got it. Thank you so much, sir.
So that's why we call it generative. See, if you wake up, you every day, your
Mhm.
child talks to you, correct? But
Right.
even if the child would ask you same question every day, you may give different answers all the time,
Yeah. Right.
correct?
Right. Right.
So
Right. Right. Got it.
similarly, yeah, because otherwise they get bored. So generative
Exactly.
models are typically designed so that you don't get bored.
Right. Yes, sir.
Correct. So it's a conditional probability distribution that you are learning from the large English text, and you are using it to generate the text. That's how we put it. So language learning is not learning the grammar or grammatical rules. Correct. So we have experienced that though we don't know grammar in detail, still we are able to construct good quality sentences in at least two or three languages. You don't have to be a grammarian to actually construct a concept, write a story, composition. And the reason is simple,
Mhm.
because you have seen lots of examples of how a particular concept is to be written. So based on your reading and based on your experiences, you can actually write a correct sentence.
Sir,
Yeah, ठीक है, यहाँ तक आई थिंक क्लियर हुआ होगा.
Hello, Dhananjay
Yeah,
sir,
hello, sir.
you are unmute
Yeah,
now.
one more question, please.
yeah, please.
Have you started this using Notepad or CMD, command prompt, or what else? This
अच्छा, ये
screen
जो
is
मैं कर रहा हूँ,
showing. Yes, yes,
this is
yes.
VS Code, VSC, VS Code.
Yes, so okay, okay.
It has a
So we
possibility
are,
of having many, yeah.
yeah, VS Code, right, right, right. So we are typing all this program here, and then how can we publish this, or there is no need to publish?
For publishing essentially means what?
So right now you are typing this all this program to this VS Code, and then after that, what we need to do?
नहीं, प्रोग्राम मतलब
अभी आपने जो ये प्रोग्राम जो मतलब जो टाइपिंग किया है जो
हाँ
x
हाँ,
माइनस जीरो जीरो इज ग्रेटर देन x, तो
हाँ हाँ
इसका
हाँ,
मतलब आगे जाके कैसे यूज होगा? राइट, दिस वन.
this one.
या राइट.
Yeah,
और
so this is
जस्ट
the essence. So I'll tell you what it is. चलिए आगे बढ़ते ही है. तो मैं अभी
यस
आपको
यस
जवाब
यस,
दे देता हूँ, फिर वापस इस पे आता है, ठीक है?
श्योर सर श्योर.
Okay, let's say I have t minus 2. थोड़ा सा आसान कर देते हैं इसको. Okay, now also let's limit our discussion to 50 by 50. Correct. So I have a vocabulary. So xk, the size of xk essentially means the different values that xk can take. xt, xt minus 1, xt minus 2. The different values it can take is, let's say, only 10 alphabets or 10 words. Correct. The question for you is, how many such entries would be there in this probability table? P is a function of three variables. P is a function of three variables. So it should be 10 cross 10 cross 10 to a probability value which is between 0 to 1. यहाँ तक ठीक है? So I take one value of xt minus 2, other value of xt minus 1, and one value of xt. and this P function would give me the probability. So it is like boy I am. So what it says is third or second word being boy, given that the first word is I, second word is am. So what it is saying is I am a boy is a sentence. X1 और X2 ये भी कर लेते हैं, ठीक. Then this becomes, just for explanation of how this function is function will be used. Okay. So what you see here is an example where I have asked a question. What is the meaning of this P? It says that what is the probability that the fourth word would be boy, given that first word is I, second word is M, and third word is A. I am a, what are the possible outcomes? I am a girl, I am a boy, I am a child, I am a fan. So it could be anything. It could be anything. That means with each of this, there is a probability associated. Let's say in my literature or whatever I have read so far, I have seen that boy appears 50% of times. Girl appears 40% of times. And the rest of the things, bat, fan, ball, and rest of things appear 0.1 times. All sum up to 1. So what language model does is it tries to learn this function P. It tries to learn this conditional probability function from the text. So more and more data is seen by this model, better and better conditional probability approximation will be available with the model. Correct. So if I show this model many English sentences, it will learn this sort of conditional probabilities. And whenever somebody shows the model I am A, it gives output which is like a probability on scale of 0 to 1 for each of this output word. So if my vocabulary is 10, I would get 10 such probability outcomes. For all 10 words, I would get a probability. The highest probability is for word boy. Now, does it make sense? धनंजय, अब ठीक है? Great. So whenever somebody says large language model, you don't have to worry about it. It is actually a conditional probability function. Now, one way would be to write down all these probabilities. अब कितनी possibilities होगी? 10 into 10 into 10 into 10. 10,000 such values would be there. Do you agree? There will be 10,000 such values. एक तरीका है कि 10,000 वैल्यूज को याद रख लो. दूसरा तरीका क्या है? You build a function. So rather than storing this as a table, use function. Use a parametric function. What is parametric function? So what it says is, rather than learning this function, rather than storing this as a table, I'll use a parametric function. So टेबल नहीं चाहिए, हम क्या करेंगे, एक इनपुट में कितने पैरामीटर्स है, 4. So I have 4 parameters with me, 4 x's with me. ये जबरदस्त है. Okay. So rather than storing this as a table, what I would do is I'll try to approximate this table with the help of a function of parameters theta. Theta essentially means the weights of your neural network. Depending on the architecture, I might have billions of weights, trillions of weights, and all these weights are part of a set which I call theta. So theta is the parameter set. When you tune this theta parameter set, you get a different probability values for your xt minus 1, xt minus 2, xt minus 3, and xt. Correct. So rather than storing a table, I learn the function approximator for the table. And this function approximator is actually a neural network. So your P is actually a neural network. So neural network is a function approximator, and that is what you use for your conditional probability distribution. Clear? अब थोड़ा सा क्लियर हुआ कि हम क्यों कंडीशनल प्रोबेबिलिटी की बात कर रहे हैं. LLM has pattern matching mechanism. Pattern matching. So if LLMs were deterministic, जैसे आपके regular expressions होते हैं, then it would be a pattern matching, correct? But here it is not pattern matching. It is essentially saying how likely this pattern is. So it is slightly beyond pattern matching. So whatever people say, whatever you come across, keep in mind, large language models are all one or the other way, they are capturing the conditional probability density function. ठीक है? So that means अगर probability नहीं पता है तो पहले probability पढ़नी पड़ेगी. So you have to first start talking about probability theory and random processes, and then you can understand the fundamentals behind training LLM, why this particular optimizer, why this cost function, why this architecture. These are the questions which will be easy to deal with when you know fundamentals of random processes probabilities. Correct. So those who are from electronics background, they would immediately realize this is like a auto-regressive process. So I know history and I want to predict the current state. This is called auto-regression, where x is a variable, x is a random process, and I have xt minus 1, xt minus 2, xt minus 3, I want to predict xt. So this is a typical example of an auto-regressive mechanism. So all causal systems, they are typically auto-regressive, unless there is some other input y. Correct. So as of now, I have not given any y as an input. LLM takes y also as an input. We'll talk about it. But as of now, this is okay. This is sufficient to begin with. Yeah, any other questions?
Participants can ask the questions in the chat box. There is one question from the Dhananjay sir. Are we able to edit this LLM if any AI tool is not answering?
Edit LLM. See, editing LLM is not as simple as changing the table. You have to change the probability values. You have to change the function approximator. To change the function approximator, you need to change the weights. Now, changing the weight would require you to access the architecture, and then you talk about changing the weights. So that is difficult task. Given a pre-trained model, it will be difficult for you to train the model because you don't have sufficient hardware for that. What you can do is you can fine tune it. So you don't take those many steps. You take a small corrective or maybe some part of the LLM. So LLM is a big pipeline. So you have lots of transformers one after the other. You can train one or two layers of your own. Others are kept freeze. That is something which you can try, which we call fine tuning. So fine tuning is possible, but beyond that, you need lot of infrastructure to train a model. And the answer that you get, if it is not as per your expectations, then probably the LLM that is being used by you is trained on a different type of context or data set. So that's why people say that foundation models should come from the domain in which you are working. So if you are, let's say, working in a medical domain and you use the English language trained LLM, it may not work. Why? Because the word A has no meaning except for being an article in English. But in medical transcription, A is like a vitamin A. So deficiency of vitamin A is very common, correct? So depending on the corpus on which the model is trained, the model would serve only that sort of domain. So there are foundation models which are trained on different domains. So you can pick a model which is based on your domain. So if you are trying to build an application on LLM for a specific domain, then you should look at what data the LLM was trained on. Yeah, so or maybe teaching purpose only. You can use the LLMs for writing codes as well. Definitely. So I'll give an example. Writing code is easy with language models, but then making sense of it is very difficult. So when you are doing it with a purpose and with some understanding, it's okay. But if somebody is trying to learn how to code, then you have to prompt LLM appropriately. Otherwise, it will give you the answer, and you will not know why it did what it did. Correct. So this tool is a good tool. Language models are good uh, in terms of enhancing your learning, but it can actually hinder your progress or growth also. So one has to be very careful while using AI tools. So this is something which I think everybody agrees and everybody knows about. So be aware of what it can do wrong. Then I think there is no harm. Okay. So I wanted to talk about perplexity because this is something which makes a lot of impact on your understanding of LLM. So let's try to motivate it from a different perspective. So when do I say a particular language model is doing good? So in terms of formal languages or compiler design, so what do we say? When somebody writes a code and it passes through the compiler checks, then I would say that this particular code is as per the language. Correct. So essentially, I have a model of a language where I have symbols, I have a way to construct new sentences, words, and so on. And if it complies with all these requirements, then I would say this sentence is actually a correct sentence of this particular language. Now, correct. So if I give English text to my model and I try to infer that whether model agrees with this text or not. How do I check that? So as I said, I have a language model with me. So what I can do, suppose I have this function with me. I have this function with me. And for time being, I'm going to use only one hop arrangement, let's say. Okay. And then I would say, find out the probability that I am a boy. What is the probability given this theta? Parametric model is there. So given this parametric model, अभी भी अच्छा वापस चला गया. मुझे तो दिखा रहा है कि शेयर्ड है. सो ठीक है. सपोज इट visible. ठीक है. Thank you. So probability that I am a boy given the model अब चला गया. अच्छा, किसी के पास जाता है, किसी के पास नहीं जाता है. बढ़िया है. ओके. हो सकता है कि मेरा ही इंटरनेट ठीक नहीं हो. देयर इज अ पॉसिबिलिटी.
Sir, you share the entire screen. So wherever you are switching, it will be visible to us.
हाँ.
Yes, visible now.
So probability that I am a boy given the parameters of the model. So parameters का मतलब क्या है? I have a network with let's say 10,000 parameters. So this 10,000 parameters are inside theta, correct? So if I want to find out this probability, what do I do? First thing is I know that this is an English language sentence, a correct sentence. So I expect this probability to be high. So I have model 1 which is characterized by theta 1. I have model 2 which is characterized by theta 2. Correct. And I try to figure out these probabilities. How do I find out these probabilities? I have transition probabilities with me. So I would first check probability of I given theta 1 multiplied by probability of m given I theta 1. Multiplied by probability of im a, and then finally multiplied by boy. यहीं तक कर लेते मल्टीप्लाई. Boy given I am a and theta 1. Correct. All these probabilities multiplied together will give me the probability of sentence I am a boy. This is called likelihood. How likely it is that I am a boy English sentence is coming out of the first neural network with parameters theta 1. Correct. So with this, I can find out likelihood of the first model. How likely it is that this sentence is actually coming out of first model. It is almost like a classification problem, correct? Then I can ask this question to model 2, second neural network. How likely it is that this comes out of second neural network? And then I can compare the first and the second probability values. Whichever is higher is more likely suitable for the text I am a boy. So if I have two different models with parameters theta 1, theta 2, the one which gives higher likelihood for actual English sentences is a better model for my English language. This is called likelihood of a sentence. Now, what I have done here is I have used the chain rule and I have assumed that यहाँ पे I am ठीक है, that this type of model is available. So I can use this model And if you allow only one transition probabilities to be stored, I can actually get rid of this. I am a boy. Correct. What it says is xt depends only on xt minus 1. It does not depend on xt minus 2, xt minus 3. So current depends only on just immediate past. It does not depend on past to past. It doesn't have a dependency on history. So only state transition probabilities. Good. So it depends on the way you have defined the model. Okay. So this is called likelihood. This word likelihood comes out of what we refer to as Bayes rule. ये याद होगा सबको. Bayes rule है probability of C given Y or X given Y is equal to probability of Y given X multiplied by probability of, ये याद है, ये हल्का सा याद होगा सबको, divided by probability of Y. Bayes rule. So I'll tell you what X and Y could be. और उल्टा कर देते हैं. For example, X could be the feature vector. Y could be a class label. So what we do is we usually say that I have observed many occurrences of a particular phenomena, or maybe if you are interested, we can talk about images or text. So I have seen lots of images of a dog, and in every dog I have seen 10 different features. So I create a vector of 10 numbers, which I call a feature vector, and I associate it with a class label called dog. Correct. So probability of class being dog given the feature vector. This is something which I want to find out. So when I see unknown feature vector, I would like to figure out whether it is a dog or not a dog. So this is a typical classification problem. And what do? We try to figure out this probability Py given X. This is called posterior probability. The right side, probability of X given Y, is called likelihood. How likely it is that I observe this feature vector given that it is a dog. So this is called likelihood. Multiplied by what is Py? It's called prior. I know how likely that I will see a dog on a road. Now, what is your take on this? On road, which probability is higher? Seeing a dog, seeing a cat, seeing a monkey, or seeing a cow? Which probability is highest? Dog, correct. So that's why there was even, in fact, a circular from Ministry of Education. स्ट्रे डॉग्स का एक सर्कुलर आया था, आपके पास भी आया होगा, हमारे पास भी आया था. सो गेटेड कंपाउंड होना चाहिए, कुत्तों को भगाइए एंड सो ऑन. दैट्स बेस्ड ऑन द स्टैटिस्टिक्स. ठीक है, वापस आ जाते हैं. सो पोस्टेरियर probability is same as likelihood multiplied by prior divided by evidence, and this is something which happens very frequently. I actually don't have to worry about evidence. So if I want to compare two probabilities, whether it is class 1 or class 2, y equals to 1 or y equals to 2, so I can actually get rid of X. For same evidence, so I observe the same feature vector. I want to find out whether it is from class 1 or class 2, dog or cat. Then its likelihood X given y equals to 1 multiplied by how likely it is that I see a dog divided by probability of X given y equals to 2 multiplied by probability y equals to 2. This is the ratio. Now what you observe in this is probability of x gets cancelled out because it is constant for both of them. So as far as this ratio is concerned, I don't have to worry about probability of x. So many a times this probability of x is something which we don't usually use. Other thing is this probability of y, if I have no clue, I have no idea whether I am in an urban setting or I am in a village setting, I cannot argue about who will be more, dog, cat, cow. I have no idea. So I would say all of them are equally likely. So under this equal likely hypothesis, entire factor becomes defunct, and your likelihood and posterior, they are similar. They are in proportion. They are same. So instead of computing likelihood or posterior, vice versa, I can actually work with likelihood. So what you are doing here is you are working with a likelihood rather than posterior. So you are taking a sentence and trying to figure out how likely it is that this sentence comes out of the model. Rather than the reverse question, given the sentence, what is the probability that it comes out of this model? So I should have been asking a reverse question, correct? Probability that I see sentence 1, I am a boy. How likely it is that this sentence comes out of model 1? I have no idea how to do that. So what I do, I flip the probabilities based on Bayes rule. And I say all the models are equally likely, all the sentences are equally likely. And so now I can talk about posterior in terms of likelihood. And that's why typically we talk about likelihood of a sentence. So how likely it is this sentence comes out of model theta 1. I hope I'm making sense. Ideally, I would have to multiply this by corresponding model probability divided by probability of a particular text. In the English language, how many times I see I am a boy, which is slightly difficult to answer, correct? So given that probability of theta 1 is same as probability of theta 2 and probability I am a boy is same, I actually don't care about this part. And so I can get rid of it. And so the posterior becomes likelihood. And then I compute this using chain rule, where I know that there is dependency of only previous alphabet or a word, a Markovian assumption. And so I can easily compute this probability given the model theta 1. So when I say model theta 1, essentially means I have a neural network where I supply a particular word, I get a probability. I supply another word, I get a probability, and so on. Good. Yeah, any questions up to this point? कोई सवाल? बस अब 2 मिनट, उसके बाद हम सीधे लार्ज लैंग्वेज मॉडल पे. या any doubts? No questions is a good sign. So चलो बढ़िया, ठीक है. So now this was about how likely it is that the text comes out of the model, which is a good idea. But so when I am training a model, so you trained your LLM, I trained my LLM, so language model, my language model, and we want to check which one is better. So you would we'll take one English corpus and try to figure out the likelihood. So you come up with a likelihood, I'll come up with my likelihood. Whichever is larger, whichever is higher, would be the winner. Correct. So that's how we treat the likelihood. Now, connected with this likelihood, there is another correction of wrong text. Okay. So answer is, I think, same as this. So when you read this, what happens? Because you have seen this word a lot of times. So you would say, in the context, A looks inappropriate. This A looks inappropriate. Correct. So the network will actually guide you saying that after D, it should be E. Sometimes it would tell you, if it is not a causal model, it would say between D and R, it should be E and not A. This is called bidirectional model. Correct. So your BERT and other things, they do have this idea of unidirection, causality. They do have the possibility of bidirectionality. So rather than just left to right, you also have right context available, and then there are missing words in between, and you try to predict this missing word probabilities. Correct. So if I make this more generic, if you allow, I would say I don't have to worry about uh, we have n length sequence, out of which I have hidden one word xk, and I want to find out how likely it is that xk is, let's say, O or U or E. Correct. So k is in between somewhere. Maybe I can make it slightly more obvious. So I want to find out this probability distribution on xk given the rest of the words. So in the context, I have every other word, but one word is missing. There is no right left. There is a context. There is a word. Correct. So neural networks are trained for this type of tasks also, where I see lot of sequences of this form. I see lots of such sequences, and then from there I learn a model. What is the model that I learn? I learn a model of this type. So I learn this model, which will spit out a probability for such sentences. From this, I can find out these conditional probabilities. So for any missing word also, I can find out the probability that which word is most likely. And so I can correct the sentences also. Same way I can correct the spellings of misspelled word also. Yeah, any questions? Hemant, is it clear? So once you understand that it is conditional probability, I think the life becomes very easy. So it is like you have lots of data points, you have lots of text. From text, you try to find out the probability distribution. And whenever some partially or some partial string of words is available, uh, you would try to figure out what are the missing word probabilities, and based on that you can figure out the correct sentence or a word. ठीक है. So this is something which I think should stay with you. The message is one liner is uh, large language model is nothing but a sophisticated uh, function approximator for conditional probability distribution. That's something which is one line definition of LLM. By the way, I can share with you a book, a freely available book online, which is a very good resource. In fact, I would recommend that you should refer to this book, and only this book, because it's a written it's written by people who actually work in this domain, correct? So it's from Stanford, and I'll paste a link here so that you can refer to it. I'll post a message in the chat. Maybe I can share that also with you. How does it look like? So this is the book by Jurowski and Martin, Speech and Language Processing. It's a third edition. Whatever I've discussed so far, it starts from chapter 1 up to chapter 4. Some portion of large language models is also covered. Transformers is something which is pending. Maybe I can help you look at this. It's a very good resource. I think you will benefit out of this. So these are the slides. One could have used this also, but this is a good resource. You can have a look at it. This is for your self study, so I'll not spend time there. Book is very rigorous in the sense that it has everything written down for you. So all the derivations, everything is there. Okay. So any questions on likelihood? I guess I think that summarizes almost everything about what we do in case of estimating the conditional probability. So estimation essentially requires you to find out these parameters. So our problem would be, I have a large corpus available. So I would state the learning problem. Learning problem is argument maximum, likelihood over all possible text sequences. Let's call them X of the language. So find out that particular theta that tuning of the parameters theta, so that maybe likelihood will be multiplied together. So multiplication is typically done by pi. Pi is for every X in the language, every sentence in the language, find out likelihood, keep multiplying them, correct? And that gives you your solution. So you find out likelihood for all sentences using parameter theta. Find out that theta which gives you maximum such likelihood. Pi stands for product over all X, product over all X's. So it's a nice optimization problem, and theta essentially means the weights, the parameters of your network, correct? So this is the learning problem for your LLM. I have lots of text. From text I want to learn theta so that my likelihood is maximum. So likelihood here essentially means P, the function P, your function P. Now likelihood is difficult to achieve, so what do we do? Replace by missing word probabilities. So instead of likelihood, I'm going to use precisely the same thing that you asked. So there are learning tasks. One of the tasks is to hide a few of the words and then train your model. Perfect. Good. So this is what a learning problem is in terms of likelihood function. Now there is another interesting parameter called perplexity. Now what is perplexity? So if I start from a word like A, where all can I go? M. Any other possibility? Suggest a possibility. I have. Then I can. Correct? This is the problem with LLM. I will. There are many such possibilities, correct? Okay. So starting from I can go to any of these words. This is called a branching factor. So from I can go to, let's say, 20 different words. So I has 20 branches to follow. Every word would be associated with its own branching factor. Based on the language English, all these sentences, I can find out how many different ways I can start from I and go forward. All of them are branches, different branches. So for every word, if I have this information, I can prepare a tree. Correct. And for this tree, I can find out on an average, every word has how many branches. Suppose I has 20 branches, R has 40 branches, name has 70 branches. I take an average over all the vocabulary, entire vocabulary. I get average branching factor. This branching factor somehow reflects the size of the tree. And it also reflects uh, the confusion that is possible because of this diversity or the different possibilities I have starting from each word. This problem of choice is something which is captured by perplexity. So if I have a probability distribution on the each of the branch, like if there are 20 words which are possible after I, and each of them has a probability of 1 by 20, then every time I draw a sample, I draw one word out of this 20, because it is equally likely if I do this 20,000 times, out of 20,000, 1,000 times I would get M, 1,000 times I would get have, 1,000 times I would get can, and so on. So it's like a mixture. I have many possibilities. But if I have a very certain sort of distribution where it says that in text, whatever I have seen, most of the time M follows I, will follows I, then the other words would have a lower or a lesser probability values, lesser conditional probability values. So when I draw from this distribution, M comes 10,000 times, will comes 6,000 times. Other words would come with, let's say, 500, 400, 300 times. Correct. So the model which actually captures the actual perplexity of the language is something which we would be interested in. So I would say that a random model would be every word is equally likely. But the moment you say it is English, which is British English, then there is certain distribution on the word usage. Correct. So it would have its own way in which M would appear after A. American English, Indian English, written English, spoken English, everything would have its own statistic. Correct. So perplexity is something which captures this idea that for a given language, how likely each of the choices, if it is known, I can find out the average branching factor based on the probability. So when I say based on probability, I am saying weighted average branching factor. And this you can prove logically. This is nothing but 1 upon the probability of each of this. You have already seen this, so I'm not going to repeat this. This is likelihood. If I have a sentence with n words, then I would say raised to n. Yeah. This is called perplexity. So given the model, obviously, what is the probability of this sentence given the model? If I find out, and why only one sentence? I would like to understand what happens to entire corpus, correct? So this will be multiplied together. So I actually do multiplication of all of this for all the sentences, and I get a score, which is called perplexity. And this is same thing as likelihood, but it is 1 upon likelihood. And to normalize it, I take a nth root of it. Okay. So with this, I think I'll stop here. I'll not move forward because, sorry, I could not cover the transformer part, but whatever I have covered, you can refer to from the book, and subsequently you can look at the transformer architecture also. It requires some exposure to linear algebra and probability theory, and you should be able to follow it without much of a difficulty. If you face any difficulty, let me know. You can drop an email also. So I'll not go forward. I'll stop here. Now, if you have any questions or doubts, feel free to discuss your questions.
Attendees, if you have any questions, you can put it in the chat box.
But yeah, no questions is the best thing I would like to have. So oh, quiz 3.
So there is one question. Any measure for the AI model accuracy?
So AI model accuracy, as I said, if you want to compare model with model, I have discussed two of them. If you don't want to compare any model, then you have to look at the loss function, how well a model is getting trained based on your cost function. So cost function is the loss, essentially loss function that you develop for your training. Based on that, you get the idea that how good your language model is getting trained. So at least on the seen or the known English text, does it give you a good likelihood, good perplexity score or not? But then there is also a possibility that people are right now after, which is you have human evaluators. So you provide lots of prompts to the LLM, and then the LLM would respond, and the human evaluator would essentially assign scores to the responses. This also is a method by which people are trying to make the, the language models better and better. Yes. Any other question? ठीक है फिर चलिए बढ़िया. I think Preeti, we are already at the end of the discussion, so we can conclude if there are no questions.
Dear participants, still, if you have any questions, you can ask to sir. Might be, sir, for few people, LLM and n-grams, that whole probabilistic part was new today, and that's why they are maybe somehow confused. Or, but no worries, whatever the books you have provided, we can have a reference for that.
नहीं अच्छा है, नहीं समझ में आया तो अच्छा है ना. So नहीं समझ में आएगा तभी तो अटेंड करना है, वरना क्यों अटेंड करेंगे? जो आता है वो थोड़ी सुनने के लिए कोई आता है. So that's good.
Yes. Just a minute, sir. Madam is joining us, Ujjwala ma'am.
Hello, sir.
Yes, madam. Namaste, madam.
Namaste, sir. Thank you very much. The session was really nice. Am I audible? Hello?
Yes.
Yes, Preeti madam, you can proceed.
Thank you, sir, once again for this nice session. You started with the basics of probability, n-grams, bigrams, and the whole things, joint probability based theorem. And obviously, whatever the book and the resources you have provided to us, all the participants are recommended to read that. So to understand the LLM concepts. So thank you very much for this nice session. So on behalf of Department of CSC Data Science, R.C. Patel Institute of Technology, Shirpur, I sincerely thanks to you for this nice session.
Thank you, Preeti ji. Thank you, Ujjwala madam.
Thank you, sir. Participants are requested to turn on your camera. We can have a group photo. Please check whether the camera, you are able to turn on the camera or not. Our day 4 will be on the rack. The session will be held by Dr. Amol Mahajan, sir. Dear participants, camera I think nahi hai. Turn on your camera. Okay, thank you to all. We can end up with now this session, and we'll look for the day 4, which is based on the RAG model, which will be a session held by Dr. Amol Mahajan sir. Thank you. Thank you for your attention. Thank you.